Every 11 years, like clockwork, the Sun undergoes a fascinating transformation where its magnetic poles reverse. This event, known as solar maximum, not only influences the beauty of auroras, but also has practical implications. From disrupting satellite communications to potentially affecting power grids, understanding these solar cycles is crucial for our technology-dependent world. Have you ever wondered how something as distant as the Sun could have a direct impact on our daily lives here on Earth? Just think about this. You're enjoying a clear evening, marveling at the vibrant hues of an aurora dancing across the sky. Little do you know, this mesmerizing display is a direct result of a cosmic phenomenon, the Sun's magnetic field flip. Join me as we delve into the intriguing world of the Sun's magnetic field flip. What does this mean for our planet? How can we predict its effects? Stick around to uncover how this cosmic ballet impacts everything from space weather forecasts to our own backyard. The solar cycle, spanning approximately 11 years, drives fluctuations in the Sun's activity levels. At solar maximum, its peak phase, intensified magnetic activity manifests through increased sunspots, solar flares, and coronal mass ejections, CMEs. These phenomena arise from the Sun's internal dynamo, where circulating charged particles generate its magnetic field. Notably, the Sun's magnetic poles reverse about every 11 years during solar maximum, a gradual process influenced by complex interactions within its convective plasma layers. During solar maximum, the Sun's magnetic field peaks in strength, enhancing the frequency and intensity of sunspots and eruptive events like solar flares and CMEs. These events can propel charged particles towards Earth, impacting our planet's magnetosphere and potentially causing geomagnetic storms. This heightened solar activity can disrupt satellite communications, GPS systems, and power grids on Earth, while also enhancing the visual spectacle of auroras, vibrant displays of light visible near Earth's poles. In essence, solar maximum exemplifies the dynamic interplay between solar dynamics and their terrestrial impacts over the course of the solar cycle. However, beyond their aesthetic appeal, increased solar activity can also pose practical challenges. Solar flares, sudden releases of energy from the Sun's atmosphere, can emit bursts of radiation across the electromagnetic spectrum. While Earth's atmosphere and magnetic field provide some protection, intense solar flares can still disrupt high-frequency radio communications and navigation systems like GPS. Coronal mass ejections, CMEs, are powerful eruptions of solar plasma and magnetic fields that travel at incredible speeds, often exceeding millions of miles per hour. During solar maximum, these phenomena increase in frequency and intensity, posing significant risks to both space and terrestrial technology. When directed towards Earth, CMEs interact with our planet's magnetosphere, potentially triggering geomagnetic storms. These storms can induce powerful electrical currents that disrupt satellite operations, damage or degrade power grids, and impact sensitive electronic equipment on the ground. Historical events like the Carrington event in 1859 serve as stark reminders of the potential impacts of severe solar storms. This event caused widespread telegraph system failures and auroras visible as far south as the Caribbean. Today, with our reliance on technology more pervasive than ever, accurate monitoring and forecasting of space weather are critical. Space agencies and scientists continuously monitor solar activity to provide early warnings of impending space weather hazards. This proactive approach allows satellite operators, power grid managers, and other stakeholders to implement protective measures during periods of heightened solar activity, minimizing potential disruptions and economic losses. In space, satellites in low Earth orbit, LEO, are particularly vulnerable to increased radiation levels during solar storms, which can degrade solar panels and affect onboard electronics. Beyond Earth, spacecraft traveling to the Moon or Mars face heightened risks from solar radiation, necessitating careful planning and monitoring of space weather conditions. Moreover, our reliance on GPS for navigation and timing synchronization means that disturbances caused by solar activity can affect sectors ranging from aviation to telecommunications. Distortions in GPS signals during geomagnetic storms can lead to inaccuracies in navigation systems, affecting both civilian and military operations. To mitigate these risks, space agencies and governments invest in advanced space weather monitoring and prediction systems. Early warnings of solar activity allow satellite operators and power grid managers to implement preventive measures, such as temporarily shutting down vulnerable systems or rerouting flights from polar regions during geomagnetic storms. Ongoing research into space weather dynamics is vital as our reliance on space-based technologies continues to grow. Scientists using advanced solar observatories and spacecraft like NASA's Solar Dynamics Observatory continuously monitor the sun's magnetic field, sunspots, and solar flares. This detailed data helps develop predictive models to forecast solar storms and their likely impacts on Earth. These forecasts are crucial for protecting satellites, astronauts, and sensitive terrestrial infrastructure from the damaging effects of solar radiation and geomagnetic disturbances. Additionally, scientific insights into solar cycles and their influence on space weather inform policies and protocols for space mission planning and operational safety, such as adjusting satellite operations or postponing spacewalks during periods of heightened solar activity. The study of solar activity and its impacts on Earth and space technology is vital for safeguarding our modern way of life. By understanding the sun's magnetic cycles and predicting solar storms, scientists and space agencies can mitigate risks to satellites, power grids, and communication systems. Continued research and investment in space weather forecasting are essential to improve our ability to forecast and prepare for these cosmic phenomena. Stay informed about the latest developments in space weather by subscribing to our channel, sharing this knowledge, and together, let's build a more resilient future in the face of solar challenges. Don't forget to like, share, and subscribe for more updates.